Okay, for yesterday's check your understanding. So this is 5.4, inverses of exponential functions. Here are the answers to number 1. You can pause the video. Okay, and here is the answer to number 2. Again, you can pause the video. It says we learned yesterday that logarithms undo exponentials by finding the missing exponent. Today we're going to explore the graphs of these inverse functions. The table below represents the function y equals log base 2 of x. Use the table to graph the function and answer the following questions. So when x is 1/4, that means 2 raised to what power is 1/4? And so we get -2. So at 1/4, we should be at -2. At 1/2, we should be at -1. So again, that's the answer to the question. 2 raised to what power is 1/2? That's -1. And then here we're looking at 2 raised to what power is 1? And so the answer to that is 0. 2 raised to what power is 2? So that's where we get 2, 1. And then 2 raised to what power is 4? That'd be 2. That's where we get 4, 2 from. If you look, what value of x would produce an output of -5? So if I want the y value here to be -5, so again, I'm going up here in this direction. And so that would be 2 raised to the -5th power, which gives 1/32. Right, this is asking log base 2 of what equals -5. And so that's, again, if you put it back in exponential, 2 raised to the -5th is what? That's where you get 1/32. So if you think about that, that's going to be way over here on the graph. So again, kind of falls in line. I can't really get it closer. It probably should be closer to the y-axis than what I drew it. 2, what's the domain and range of this function? So hopefully you can kind of pick up on some of the characteristics, what this graph would probably look like. So it would look something like this. So our domain, that's the list of possible x values. There's a vertical asymptote here at the y-axis. So the domain is from 0 to infinity. The range is a list of y values. It goes down forever to -infinity. And even though it looks like it's kind of plateauing, there is no horizontal asymptote. It will continue to grow. It just grows kind of slowly. So it's from -infinity to +infinity is the range. Or another way to say that, it's all real numbers. So how are your answers to question 2 related to the domain and range of y equals 2 to the x? So here, this is our exponential function we've been looking at previously. So for the exponential function, the domain was -infinity to +infinity, and the range was 0 to infinity. So hopefully you can kind of make that connection that the domain of a logarithm is the range of the exponential, and the range of the logarithm is the domain of the exponentials. We're just changing the x's and the y's because they are inverses. So the domain and range are switched. And so right here, let's look back at the graph really quickly. This is the graph of y equals log base 2 of x in red. If I was to graph y equals 2 to the x, if you think about that, think about our values again. If I plugged in -1 for x, I would get a half. If I plugged in -2, I would get a fourth. If I plugged in 0, 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. And again, hopefully you kind of know what a 2 to the x graph looks like. So if I connect those points, that's kind of close right there. And just again, imagine if I drew the line y equals x, that it's a reflection over that line, which again is another way to signify that these are inverses of each other, a logarithm and an exponential. Okay, here we've got the graphs of 3 different parent logarithmic functions are shown below. So looking at that, what could we say that all of these graphs have in common? Well, hopefully you see they all have vertical asymptotes at x equals 0. So I'm going to abbreviate that VA at x equals 0. They all are increasing forever. And looks like they all have a point in common here at 1, 0. So they all have the point 1, 0. So they all have the same x-intercept. B, the equations for the 3 graphs are y equals log of x, y equals log base 4 of x, and y equals the natural log of x. Which is which, and how do you know? So I'm going to use color here to do this. So if I'm looking at y equals log of x, that's an understood base of 10, right? Even though we don't write the base, there's an understood base of 10. So I know that the blue graph is asking 10 raised to the y equals the x. So what I can think here is when the y value is 1, 10 to the first would be x. So I expect when the y value is 1 that the x value should be 10. Does that make sense? Hopefully to everyone. So I'm looking at this point right here. Because there's only one of these graphs that goes through that point. This one there, the blue one, is log of x. And here let's do red, and I would use the same kind of thinking. 4 raised to the y equals x. And so when the y value is 1, I expect the x value to be 4. So that's happening right here. So that's the second one. And then the last one, if I'm looking at y equals the natural log of x. So remember, natural log has an understood base of e. So this is saying e raised to the y power equals x. And so let's just imagine when y is 1, so e to the first power, and let's see what's that output. It looks like it's somewhere between 2 and 3, right? Which, if you remember when we learned about E, that's where it should be. E's like 2.717 something. And so how did we do this? So how did we know? Well, we plugged in 1 for y and determined where the correct x value would be. It says use the graph to estimate log base 4 of 6. So I know log base 4 is my red graph. And if I'm finding log base 4 of 6, so again, what's this asking? This is saying 4 raised to the y. Where's that equal to the x value, which in this case is 6. Write the x value 6 here. So if I go to where the x value is 6, what's the y value for the red graph? It looks like I'm somewhere between 1 and 1.5. So I could say that the y value is approximately 1.3. And so again, what's this saying? This is saying 4 raised to the 1.3 is equal to 6. And again, that's just a rough estimate because it's hard to get an exact point from that graph. And a couple more things that they wanted me to add over here that's in the red to go with that. Log base b of 1 equaling 0. So it doesn't, what they're saying is it doesn't matter what the base is. If I took that base and raised it to the 0 power, I should get 1. And so that's why all of the graphs went through 1, 0. Because when the argument was 1, the only possibility is an exponent being 0. Because anything raised to the 0 power gives 1. So this here is explaining why they all have an x-intercept at 1. And then right here, b raised to the first power is b. So kind of what you're looking at here, if I'm taking log base b of b, we can kind of think of that as canceling out and becoming a 1. So like if I had log base 4 of 4. This is saying 4 raised to what power is 4. And so as we work more of these problems, we'll automatically see that log base 4 of 4 simplifies to be a 1. And we kind of understand why, because, again, if I'm taking the base, raising it to what power gives me that base back. It has to be a 1. Let's just go ahead and look at 5 together. Hopefully you kind of are good at answering this first one. If I started with my parent function being y equals log base 4 of x, and I want to move it right 3 units. So shifting right would affect the x's. The x's are on the inside of the function, and they do the opposite from what you think they should do. So if I need to go right 3, I need to subtract 3 on the inside. So again, hopefully that's kind of makes sense. And then how does this transformation affect the x-intercept, the asymptote, the domain, and the range? So let's think through what would happen. So normally, all logarithms we know have an x-intercept at 1, 0, and they have a vertical asymptote at x equals 0. Right? Those are the main characteristics that we looked at that were common with all logarithms. If I shift the graph right 3, that is going to move the x-intercept right 3. If I shift the graph right 3, that's going to move the vertical asymptote right 3. If I shift the graph right 3, that would affect the domain. Instead of being from 0 to infinity, it's now from 3 to infinity. because we are moving that vertical asymptote over. The whole graph, all of its key characteristics get shifted right. But now moving something to the right that goes from negative infinity to positive infinity, in the range, right, in the y values, has no effect. So this didn't change the y's at all, which again makes sense. It was on the inside. The inside affects x's, does not affect y's. So the range would still be all real numbers, or negative infinity to positive infinity. So your transformations here of logarithms, they only affect the x-intercepts, the vertical asymptote, and the domain. Okay, here is your quick notes. I'm trying to look over them really quickly, see if there's anything that we really haven't covered yet. Most of this stuff we kind of talked about. They kind of go in more detail with the key points and showing their inverse being reflected over that line, y equals x. Now look here, b raised to the x and log base b of x are inverses. So that means e to the x and log base e of x, which we can write as natural log of x. Those are inverses of each other. They undo each other. Okay, what I want you to do now is go ahead and try to check your understanding. I'm going to put the answers up. So go ahead and pause the video. So here's number 1. So you can see they make you do a transformation on the inside. Inside affects x's. So if there's a negative, that means I multiplied by -1 that affects the x's. That's a reflection over the y-axis. Right, that changes the signs of all the x's. So hopefully you see that. Vertical asymptote didn't move. The x-intercept used to be at 1, 0, now is at -1, 0. The domain used to be the positive numbers, now there's just the negative numbers. So from negative infinity up to 0. And again, the range was unchanged. Here you're matching graphs with their transformations. So again, the ones that to me would be the easiest to find are these where we're shifting the graph. This one's shifting the graph up 5, and then it's being reflected. Here we're shifting the graph down 5. So again, if I go up 5 and reflect it, here this one should be B. I see how the x-intercept used to be here 1, 0. I can see I moved that up 5 roughly, and it's reflected going the other way. So this one's B. Here this one shifted down 5 and then being squished. Right, it's got a my brain's not working. It's got a compression of 1/2. So that one's here. That's the one that shifted down 5. This one here, I need to go right 5. So I should move the vertical asymptote right 5. The only one that does that's A. So again, those to me are the easiest to pick out. And so now I'm just picking between C and D. And again, look at the number out front. This one has to be reflected. So it's an upside down logarithm. So that one has to be D. And then this one has just been stretched. So it should look like a regular logarithm. Except it's, like I said, you pulled that flat part up by stretching it. Okay, here write an equation for a logarithm that has a vertical asymptote at x equals 5 and goes through the point 11, 1. So to get the vertical asymptote at x equals 5, you have to move the graph right 5. There's no other way to do it. So you got to have a -5 on the inside to do that. So now they've got log base b. That means we don't know the base of x minus 5. That's shifted the graph right 5 equals y. So if I take this and rewrite it from logarithmic to exponential, this is the base raised to the answer. So b raised to the y equals x minus 5. Well, now, so they didn't really write that down, so let me write that. B raised to the y equals x minus 5. So there are three unknowns here, an x, a y, and the base, b. Well, the thing is, they give me an x and a y that makes it true. So if I plug those in, make this become b raised to the first equals 11 minus 5. Now I just have one unknown. So b to the first is b, 11 minus 5 is 6. So now I know that the base must be 6. And so it's y equals log base 6 of x minus 5.